Greetings, Colloquium attendees. My name is Joaquin Marcelo, an advisee of Professor Ryan C. Mailem, and it's an honor to have you stop by and watch the presentation of my submission for the CBMES 72nd Research Colloquium entitled The Design and Performance Analysis of a Novel Energy Harvesting Smart Stent, a combined CFD and FEA investigation. So let's get right into it, shall we? Now, stenting is an indispensable part of interventional cardiology, addressing the critical need to restore adequate blood flow in vessels afflicted by vascular stenosis. Vascular stenosis often stems from the accumulation of plaque composed of calcium, cholesterol, and other cellular debris within the artery's inner lining. Left unchecked, this buildup could lead to severe consequences like the formation of blood clots, which typically lead to the subsequent partial or complete obstruction of blood flow to vital organs, leading to life threatening conditions such as heart attacks and, as you know, strokes. Fortunately, the landscape of cardiovascular treatment has been largely influenced by advancements in stent design research, with many contemporary efforts concentrated on refining existing stent designs through computer aided means and exploring drug eluting capabilities to minimize the occurrence of these complications. This includes enhancing stent biocompatibility, mitigating inflammation at the site of implantation, and reducing the risk of restenosis or the re-narrowing of an already treated artery. But despite significant strides in stent design, a notable gap persists in the integration of both sensing components and energy replenishing elements into these biomedical devices with long term applications in mind. While current stent technologies excel in restoring blood flow and mitigating stenosis related complications, they lack the capability to provide real time information on the stent status post implantation. I think that this presents itself as a significant limitation in cardiovascular care. Without the means to promptly detect and address these potential complications, patients are left vulnerable to unforeseeable events such as restenosis, thrombosis, and even stent migration. By equipping stents with the ability to monitor vascular health and detect anomalies in real time, clinicians can proactively provide intervention to prevent or mitigate the progression of complications. As if to say that early detection of issues allows for timely adjustments in treatment strategies. This study aims to address this existing research gap by exploring the feasibility and efficacy of integrating piezoelectric sensing components into various pre existing stent designs. Now, cardiovascular diseases, including ischemic heart disease and ischemic stroke, collectively impose a pretty substantial global health burden, contributing to the elevated yearly morbidity and mortality rates worldwide. According to Johns Hopkins Medicine, approximately 87% of all strokes are attributable to the obstruction of blood flow to the brain. Conversely, ischemic heart disease, which is defined by the congestion of blood supplied to the heart, is said to have affected over 244.1 million individuals in 2020, resulting in approximately 19.1 million deaths by 2022. By focusing on advancing on stent technology, this study, whether directly or indirectly, imparts a positive effect on prospects for the treatment of these life threatening conditions, aiming to enhance patient outcomes and subsequently alleviating the strain that exists upon our healthcare systems. Why? Well, because smart stents can provide clinicians with invaluable information about the condition of the patient's vasculature, facilitating early detection and offering early intervention in the event of a complication. This proactive approach to patient care could not only improve treatment efficacy, but also enhance patient safety and satisfaction. Additionally, the self sustaining functionality of smart stents reduces the need for frequent interventions and follow ups, streamlining the delivery of healthcare and optimizing the utilization of clinical resources. Now, the primary objective of this study is to create a comprehensive model that creates room for the integration of both sensing capabilities and energy harvesting mechanisms. By leveraging insights from existing research designs, the study seeks to establish a robust framework for the development of a conceptual smart stent model, theoretically capable of real time monitoring and self sustained operation. Then, by creating analogous models with slight variations in its material properties and geometric parameters, it is possible to explore the optimal configuration for the designed smart stent, in terms of its finite element analysis at least. By systematically varying these factors, I would be able to identify the most effective combination that maximizes performance without sacrificing structural integrity. Lastly, by quantitatively evaluating factors such as blood flow patterns, pressure gradients, and shear stresses in both ANSYS Discovery and Fluent, it then becomes possible to assess the efficacy and superiority of the smart stent design in facilitating optimal hemodynamic conditions within simulated vasculature. But that's only the beginning. And as far as I'm concerned, this is just the boring part. So why don't I show you how I turned my vision into a reality? In my pursuit to innovate on medical stent technology, I had designed and evaluated 18 unique stent variations, focusing on different stent geometries and materials. Using Autodesk Fusion 360, I created variations in three specific parameters: wire revolutions, wire count, and the material of composition. Wire revolutions dictates the number of times that any given wire revolves around the central axis, and it's divided into three groups, being zero point 0.5, 1, and 1.5 revolutions. Wire count, on the other hand, dictates the number of wires present in each stent. Both of these variations were then carefully designed using both 316L stainless steel and a cobalt chromium alloy. I then tested each variation for its mechanical characteristics by allowing the model to experience a uniform pressure load applied to the outer surface of the cylinder at a force of 0.0159987 megapascals, or approximately 120 millimeters of mercury, replicating the physiological conditions of human arterial blood pressure. I had then collected and tabulated the data in order to define the best performing variation, which in this case is our stent featuring zero point 0.5 revolutions with 24 wires made in 316L stainless steel. After which, I had integrated the piezoelectric curved beam energy harvester to the proximal side of the stent along with a microelectromechanical system pressure sensor at its opposite distal end. Both components were designed based on pre-existing literature. The harvester, made of polyvinylidene fluoride, had been attached by extending six of the wires by zero point 0.3 millimeters to retain the harvester's ability to bend. Conversely, the sensor, made of silicon nitride, was attached directly to the bottom of the stent by virtue of laser micro-welding. The newly designed device was then resubjected to mechanical pressure testing to evaluate its updated mechanical parameters in terms of both stress and deformation. The model was then imported into ANSYS Discovery, subtracting its geometry from a cylinder that's 3 millimeters in diameter. Utilizing a user-defined fluid with a density of 1060 kilograms per meter cubed and a viscosity value of 0.0035 pascal seconds, it is possible to emulate the physiological conditions of blood as a Newtonian fluid. A flow inlet had been situated at the end of the cylinder in which the harvester is found. The user-defined fluid enters the system at this inlet with a velocity of zero point 0.4 meters per second, representing typical arterial blood flow conditions in a simplified form. The figure presented above illustrates a particle simulation showing blood flow velocity within the stent, categorized into four different groups and presented in both an isometric and cross-sectional view. The visualization reveals that blood flow velocity near the stent's walls is significantly lower at about zero point 0.1 to zero point 0.3 meters per second due to the frictional forces, while the velocity near the stent's axis is higher due to the minimal interference, which in this case is about zero point 0.5 to zero point 0.7 meters per second. But in order to create a truly comprehensive and realistic analysis, it's important to define our fluid based on parameters that are more complex than a set of simple constants. In this case, I had integrated the use of user-defined functions for emulating nonlinear parameters such as the pulsatile nature of our inlet flow velocity and the non-Newtonian behavior of our fluid using the equations implied by the Casson model to represent viscosity based on shear rate derived from the hematocrit and the base viscosity value. Incorporating these functions into a repeat simulation in ANSYS Fluent, I had been able to generate more realistic results by mimicking the physiological conditions of the non-Newtonian pulsatile and laminar nature of fluid when it is situated inside the artery. The cross-sectional contour plot displayed above exhibits the parabolic velocity profile that is characteristic of laminar flow. The profile bends in one direction due to the asymmetrical distribution of shear forces cast by the opening of the curved beam harvester situated at the upper side of the plot. The higher velocity gradient near the device's walls exhibits the shear thinning nature of a non-Newtonian fluid. The velocity profile is much less defined in the area enclosed by the stent due to the disruption of flow created by the stent struts, leading to a more homogeneous distribution of velocity. Subsequently, the contour plot for pressure reveals that a high pressure region is developed near the harvester, which gradually transitions into a low pressure region as it heads for the sensor side of the stent. This area of higher pressure originates from the obstruction created by the harvester, increasing local pressure. Additionally, a thin band of high pressure exists in the area immediately downstream of the harvester. As blood flows past the harvester, however, the pressure gradually decreases, leading to the progressive transition observed in both views. Lastly, the contour plot for wall shear stress predominantly depicts a uniform dark blue color, indicative of low shear stress across most of the stented area. However, regions adjacent to the stent's wires exhibit a notably higher wall shear stress, peaking at a value of over 9.6 pascals. The resulting fluid dynamics created by the novel stent design reveals a distinct profile where fluid velocity is concentrated along the central axis of the cylinder. As the fluid progresses distally toward the integrated MEMS pressure sensor, the pressure built up at the harvester gradually dissipates throughout the length of the stent. The device as a whole demonstrates low wall shear stress. However, through the length of the stent's wires, the velocity is thoroughly dissipated and more evenly distributed, resulting in its blurry velocity profile. Wall shear stress is highest in the regions between the stent's wires, with the maximum recorded value reaching over 9.6 pascals. The fluid dynamics in the area surrounding the MEMS pressure sensor indicate that the region experiences negligible changes in velocity, pressure, and wall shear stress. As for my recommendation, in order to further enhance the design, it is recommendable that future iterations modify the piezoelectric harvester so that the face perpendicular to the flow feature a rounded or beveled edge. This modification could likely lower the pressure readings and reduce velocity spikes in the region enclosed by the harvester, theoretically improving fluid dynamics and reducing stress induced wear. Future studies should also acquire more physiologically accurate arterial geometries from real CT and MRI scans as references for the affected vasculature, providing a more realistic basis for simulation and analysis. Additionally, further research should compare the performance of the proposed novel device along with any future improvements with that of a standard stent to better understand their comparative efficacy and potential advantages in clinical applications. Together, these recommendations aim to refine the device design and improve the accuracy and relevance of future studies, contributing to the advancement of stent technology and better patient outcomes. Thank you for watching my participation to this year's CBMES Colloquium. My name is Joaquin Lorenzo Di Marcelo, and I'd love to hear your thoughts, questions, and opinions in the discussion down below. Thanks for watching.